Today's lesson we're going to actually split into 2 days. So today will just be day 1. We're going to focus on when chords intersect on the inside of the circle. And then day 2 will be next week. We're going to focus on when chords, secants, tangents intersect outside of a circle. So you may remember when we talked about other angle relationships, we talked about inside, outside, and on the circle. So with chords intersecting with segment lengths, we really only need to talk about inside and outside the circle. You may see some familiarity. Sorry, I can't talk right now. You may seem a little bit familiar to the discovery that we did a few weeks ago with the GeoGebra and the lengths of segments, and you filled in a table to kind of try to see what was going on with them. So hopefully you can draw back to your previous knowledge from that discovery activity to help you accomplish today's lesson and next Monday's lesson. Okay, so again, all these relationships are on that formula sheet. So if you do have a copy of that, or if you want to refer back to that, feel free to use the formula sheet to help you with that. Okay, so just a reminder, a chord is a segment whose endpoints are on the circle. When two chords intersect in the interior, again, we're focusing strictly on inside today, each chord is divided into two segments that are called segments of the chord. I always think children of the corn when I say this. So they are called segments of the chord. Okay, so let me look at this diagram to kind of tell you what I mean. Segments of the chord. So looking at this diagram, you can see we have one piece here. We have one piece here. So the blue would be a segment of chord DC. It's a piece of it. The green would be a segment of chord DC. It is just a piece of it. We also have a segment of the chord here. That is a piece of chord AB. And we have a segment of the chord here. EB is a piece of chord AB. So segments of the chord are just showing you all the different pieces that there are. Okay, so each of those different colors is a segment of a chord. Okay, so when they intersect on the interior, again, we're focusing solely on interior today, the product of the lengths of the segments of one chord must be equal to the products of the lengths of the segment of the other chord. So I don't know if you can see this underneath here. I'll write it a little bit bigger, but this says AE times EB. So again, those are the two segments of chord AB. So this is AE times EB equals, and then it says CE, which is the one that we highlighted in green, times ED, which is the one that we highlighted in blue. So that equals CE times ED. Okay, so you multiply the two pieces of each chord together and set them equal. That's a relationship that has to happen when you have two chords intersecting on the inside of a circle. Okay, so let's look at some examples here. So in example 1, we have 4 segments of the chord again. I'm just going to highlight them so you know where I'm getting this information from. Because these chords are intersecting in the interior or inside the circle, I know that I have to multiply the two pieces of each chord together. So I know that x plus 2 times x plus 1 will have to equal x times x plus 4. So I color-coded that so you can kind of see where from the diagram I'm getting that. So we do need to remember some algebra here. Okay, so on the left-hand side, we're going to FOIL this out. You should hopefully be able to FOIL. Right, so that was first, outer, inner, last. I already went ahead and combined like terms to get that 3x. Right, on the other side, we don't need to FOIL, but we do need to distribute. We get x squared plus 4x. Okay? And these are equal to each other. So our goal is to be able to solve this. Do not let the x squared scare you. I know a lot of you may not remember how to factor and solve by factoring. We're not going to go quite that far. Okay, but we are going to go ahead and get all of our like terms together so they actually cancel out for you. So you don't even need to worry about the fact that this was originally a quadratic. And then if we subtract it over, we get 2 equals x. Okay, but we are not quite done. Notice up here they asked us for ML, which is, actually let me highlight that in blue and green because ML is the blue and green together. So I'm going to take that value that I got for x, which is 2, and I'm going to plug that back in. So if x is 2, that means this is 4. If x is 2, that means this is 3. So that means ML, if I add them together, 4 plus 3 is 7. So green, and I'll highlight that in blue so you know which ones I did to do that. Okay, now again, I got x equal to 2. So if I plug that back in, that means this little piece is 2. And that means this little piece is 6. So again, I'm going to highlight JK in yellow and red just so you know which ones I'm looking at to get that. So then when I add 2 and 6 together, I get 8. And I'm going to highlight that in yellow. So again, the color scheme matches. Okay, so you multiply the 2 pieces of each chord, set them equal, and solve that equation. We're going to go ahead and look at another one here. Example 2. Again, I'm going to highlight each segment of the chord in a different color just so we can kind of see where we're getting our numbers from and what kind of goes with what here. So because these chords intersect on the inside, I know I need to multiply each piece together. So I know that x, I'm going to have to multiply by 4x. And I know that 3x, I'm going to have to multiply by x plus 1. And then again, go through the algebra. So here we have x times 4x will be 4x squared. On the other side, if I distribute, I'm going to get 3x squared plus 3x. Okay, and now I want everything on the same side. You may remember with quadratics, it does need to equal 0 before you can begin to solve it. So I'm going to get my x squareds on one side. And I'm actually going to get everything on the same side. So I'm going to subtract 3x over as well so that it equals 0. So you might notice there is a GCF here. Between x squared and 3x, the x factors out. So we get x times x minus 3 equal to 0. And then that means that x equals 0 or x equals 3. Okay, so the x equals 0 doesn't really make sense for this because the diagram does exist, so x does have a non-zero value. But again, we're not just asking for x, they're asking us for some specific values. So they're asking us for RT, which is the yellow and the red together. So if I plug in 3 for x, that means 3 plus 7 is 10. 3 plus 7 is 10. And 3 times 3 is 9. So if I add those together, I will get 9. And again, try to keep these colors together for you so you know where I'm going. And then for SU, well, that was the green. Nope, green and the blue together. Okay, so if I know that x is 3, that means this part here is 3. And that means this part here, 4 times 3 is 12. If I add 3 and 12 together, that was supposed to be blue, sorry. If I add 3 and 12 together, that gives me 15. Okay, so I know it can be a little bit tedious, but multiply each segment of the chord together for each chord and then set them equal and solve. I'm going to give you a chance to do one more example. So for this example, I would encourage you to try it yourself. So pause the video, try it yourself, see if you can figure it out, and then come back to see if you get it correct. So just like before, I am going to highlight each segment of the chord in a different color so you can hopefully kind of see what I'm doing and where I'm coming from. So again, these chords do intersect inside, so that means we're going to be multiplying them, the two pieces together. And then we had 9 times 16 on this other side. Okay, so 18 times x gives me 18x. 9 times 16, let me do that quick. 9 times 16 is 144. So then to get the x value, we just need to do 144 divided by 18. So my x equals 8. So this one's a little bit more simple. There's no algebraic expressions, just some straight up numbers and only one variable. Okay, so hopefully that makes a little bit of sense. Please let me know if you need help. Thank you so much. Have a great day.